Hello and welcome to this video about the inverses of matrices. In this video we will learn what matrix inverses actually are by multiplying matrices together in different ways. Matrices were designed to solve systems of linear equations like the ones displayed here, and these sorts of systems with many more variables, sometimes 100 or more. These two equations can be packed up into this matrix vector equation that is written here. Vectors are a type of matrix with only a single row or column. Matrices generally refer to matrices whose number of rows and columns are always 2 or greater. Vectors can be treated as a type of matrix. This matrix equation may be multiplied out, that is, the matrix and vector can be multiplied together to give this vector equation, which is very similar to the first set of equations. The second equation may be rewritten as an augmented matrix, with a bar separating the two halves of the matrix that are set equal to each other. The variables have been completely ignored. It is supposed that when you make an augmented matrix, then you can remember which variables you are using and can type them in later. So now to solve this system of equations, we'll solve it using the augmented matrix because there is much less writing, only filling in of numbers in the matrix. We'll do this using row operations. The first of these operations is to divide every element in the first row by 2. This is to make the leading element equal to 1, and because the leading element at the moment is 2, then this is the number to divide the row by, to make the leading element equal to 1. We'll write out the operation, all of the numbers in the first row being divided by 2. And so this is the first matrix after this row operation, with the leading element being equal to 1. The next operation is to make the rest of this column contain 0 entries. We'll do this by subtracting 4 times the first row from the second row. And this is the operation in a form so that we can see how it's done. This is the matrix after the second operation. These two operations can be combined into one pivot operation, which is the operation which creates a column with a leading 1 and the rest of the entries being equal to 0. This is better shown in a 3 by 3 matrix, but a 2 by 2 matrix should be enough for now. Now to get the next leading 1 in the next row, we do this by dividing the second row by -1. It's better to write it out like this, because it is more systematic and better describes what we're trying to do. We'll just write out the operation in full. And so this is the augmented matrix after the third row operation. I'll just write it out again here and create a bit more space. The next row operation is to eliminate the 1.5 from this matrix. We'll do this by subtracting 1.5 times the second row from the first. And so we'll write this row operation out in full. You should be able to see how this particular element is going to be set to be a 0. So this is the solved augmented matrix. We can say that it's in reduced row echelon form. The first 2 columns make up the identity matrix, which is a matrix that will always multiply by another matrix to give the same matrix. It behaves like the number 1 in the real number system. This means that we have a unique solution. We have a solution and there is only one solution. We can write this augmented matrix out as this matrix equation, easily remembering what the variables were. We can see that the vector xy is multiplied on the left by the identity matrix, which is like the number 1 in this equation. Multiplying this matrix by the vector gives us this vector, which simplifies to be this equation. We can then unpack this vector equation to give us these two equations, which are the solutions to the first two equations. It does look over messy to do this with two variables, but this method can work for 5, 6, or even hundreds of variables very easily, and a computer may be programmed to do it. These row operations can be represented by matrices. This is the matrix that corresponds to this row operation. It is a diagonal matrix with only one diagonal entry that isn't equal to 1. We can multiply this matrix on the left-hand side of the augmented matrix to apply this row operation to it. This is the effect of left multiplication on this matrix. Its behavior under multiplication is just like on any 2 by 3 matrix. The long bar inside this matrix has no effect on multiplication. And so this is what the matrix is after being multiplied by this row operation matrix. It's just the same as applying the row operation itself. Now to look at this row operation, which is row addition. It's an identity matrix with an extra non-diagonal entry that's equal to the number we are multiplying the row by before we add it. When we multiply it by the augmented matrix, it should have the same effect as performing the row operation on it. This is how we multiply this matrix by its row operation matrix. And so multiplication by this row operation matrix is the same as applying the row operation itself. Here is another row operation that we haven't used yet. It swaps two rows with each other. This is what a row swap matrix looks like. There is only one pair of rows that can be swapped in this matrix, so there is only one row swap matrix for any 2 by 2 matrix. We apply the row swap operation to this augmented matrix by multiplying it on the left. We can see in this example that the first row can't have a leading 1 unless the two rows are swapped, because there's a 0 where the leading 1 should be, and nothing can be multiplied by 0 to give 1. And this is what a row swap operation matrix multiplied by an augmented matrix looks like. So this is the answer. You can see here that both rows have been swapped. We can perform a batch row add on this 3 by 3 matrix, so that all of the rest of the entries underneath the leading 1 in its column will be made equal to 0. This is what the batch row add matrix looks like, with a -5 and -8 in the first column corresponding to the 5 and 8 in the augmented matrix. This is because we want to subtract 5 and 8 from the first element in these rows. Applying the row operation does this subtraction, so that all of the other entries in this column are now equal to 0. Applying all of the row operations to this matrix so as to get the solution to these equations represented by this augmented matrix is just like multiplying all of these matrices together. The left-hand side of this final augmented matrix is the identity matrix. These row operation matrices may be multiplied together before being multiplied by the augmented matrix to give one matrix. And this matrix is the inverse of this square matrix that is contained inside the augmented matrix. This is how to get the inverse of a matrix. And evaluating it gives us this matrix as being the inverse. To be a proper inverse, it should multiply by the matrix that it is an inverse of on both sides. It should be both a right and left inverse. We'll just look at how this inverse matrix solves the equation represented by this augmented matrix. If we multiply it on the left by this matrix, then it gives us this solution matrix, which is an augmented matrix having the identity matrix on its left side. The solution to these variables x and y are on the right. Even though x and y aren't explicitly written here, we can remember setting this augmented matrix up to solve these two variables. This is what the inverse matrix is equal to in terms of an actual matrix whose entries are known, so that we can perform the multiplication. And this is the matrix equation that this augmented matrix represents. When we're multiplying the augmented matrix by this inverse matrix, then this is what we're actually doing. We're multiplying both sides of this equation by the matrix inverse. And after multiplication by this inverse, we get this matrix equation. Multiplying the identity matrix by this vector containing variables gives us this vector back, because the identity matrix behaves like the number 1 when we multiply it by anything. Unpacking this vector equation gives us these two equations, which are the solution to this problem. Here's another way of looking at matrix inverses. We can have a matrix multiplied by a vector of variables to give a second vector of variables. Multiplying the matrix by the vector gives us this vector equation, where the columns are marked by these variables. Then multiplying both sides by the inverse matrix gives us this matrix equation. To do the multiplication, we need to know all of the entries of the inverse matrix. We'll set out the multiplication here, showing the different entries being multiplied together. After simplifying the left-hand side quickly, we get this as the left-hand side. The left-hand side vector is equal to just x and y. So we can see here that the inverse of a matrix is also the inverse of the function. If the variables a and b are a function of x and y represented by a matrix, then x and y are a function of a and b, and are represented by the inverse of this matrix. It is a way of going in reverse. We can get a and b from x and y, and then get x and y from a and b back again. Now to look at the row operations in two different representations of these equations. We'll start off with this representation where the matrix is already multiplied by the variables on the left-hand side, and we'll run a solution in parallel on the right-hand side, represented by this augmented matrix. We'll perform a row multiplication operation on this first representation by multiplying it by this row operation matrix on both sides of this equation. And this parallels with this row operation matrix being multiplied on the left-hand side of this augmented matrix. Simplifying the equation on the left-hand side gives us this vector equation. And multiplying these two matrices together gives us this augmented matrix. You should be able to see the similarities between these two equations. They contain the same numbers, only set out a little bit differently. We'll rewrite the new equations out again on the top of the screen, so we can get ready to perform the second row operation on them. This is a row add operation to eliminate the 4x in the second line. We'll do this by multiplying both sides by this row operation matrix. And similarly, we'll multiply these two matrices together. After performing this row operation, we have this vector equation. I've written it in a form that isn't usually done in algebra. I've written the coefficients 1, 0 and -1 in front of these variables. I've done this so I can compare these numbers with those found in the augmented matrix. And multiplying these two matrices together gives us this matrix. Can you see the similarities between the two equations? That they contain the same numbers, and that multiplying these two matrices together like this is doing the same things to both systems of equations. Now we need to perform a row operation to make the coefficient of y equal to 1 on the second line. This is the row operation that performs this function. It is a second row multiplication operation, and multiplying all of these matrices out gives us these matrices. And now for the last row operation. We need to eliminate the y term in the first row. We do this by multiplying it by this row operation matrix. And now the matrices are in the simplest form. We say that the augmented matrix is in reduced row echelon form. Simplifying the left-hand side gives us this equation, which is good enough to be the solution. Now to have a better look at the inverses of matrices. The inverse of a matrix should multiply both on the left-hand side and on the right-hand side to give the identity matrix. We'll look at the left-hand side first to see if it is a left-hand inverse. Multiplying two matrices together gives us this matrix with these entries. And evaluating these entries gives us this matrix, which is the 2 by 2 identity matrix. This is the matrix equivalent of 1. So this inverse matrix is a left-hand inverse. We can quickly have a look if it's a right-hand inverse, and because it multiplies on the right to make the identity matrix, then it is also a right-hand inverse. So because it is both a left and right-hand inverse, then it is an inverse of this matrix. Now to have a look at multiplication by the left inverse again, but after the matrix has been multiplied by the vector xy. This should help you to see how a matrix inverse works a bit more. Multiplying the matrix by the vector gives us this vector, which looks a bit messy and needs to be simplified. We can gather all of the coefficients of x and y together. The x and y variables act as placeholders, so that the matrix and vector can be multiplied as though the vector was a matrix, with x representing the first column and y representing the second. And simplifying this vector gives us this vector, which is written like this so as to look a bit more like a matrix, and like the identity matrix in particular. So this inverse is a left inverse. This vector can be further simplified to be this vector, which is the identity matrix multiplied by the xy vector on the left. Now to have a look at why inverses are both left and right inverses. We'll start off with this equation here. This series of row operations multiplied on the left of this matrix form an inverse, and then multiply on the left of this matrix to give the identity matrix, which is the matrix version of 1. This matrix itself can be rewritten as this string of matrices, the inverse row operation matrices in reverse order. Multiplying the inverse on the left gives the identity, which I can demonstrate more clearly a bit later, because each matrix can meet up with its inverse and multiply together to make the identity. And the inverse can multiply on the right of this matrix, because each matrix will similarly meet up with its inverse to eventually give the identity matrix. So now to look at just how these matrices multiply together to eventually give the identity matrix. We'll start off with this equation here, with the inverse being these 4 row operation matrices in front of the matrix that it's an inverse of. Now we'll substitute in these inverse row operations for this original matrix. The two middle matrices multiply together to give the identity. This identity will multiply by the matrix on either its left or right side, so as to give this matrix back unchanged, resulting in this identity disappearing. And these two middle matrices multiply together to give the identity, because one is the inverse of the other. And this identity vanishes like it did before. I'll just rewrite it again up here. These two matrices in the middle multiply together to give the identity matrix, because they are inverses of each other. This is the third time this has happened in this calculation. And this identity vanishes again, because that's what ones do in multiplication. And finally, these two matrices multiply together to make the identity, because they are inverses of each other. But this time the identity doesn't vanish, because there isn't anything on either side of it to multiply by. So the identity is the solution, which means that the multiple of all the row operation matrices is the inverse of the original matrix that we started with. Now to look at the more formal method of finding the inverse of a matrix. This is done by constructing an augmented matrix that is formed by joining two square matrices together as so, with the matrix that we're going to find the inverse of in the first half and the identity matrix in the second. We'll perform row operations on the whole of this matrix, which is a 2 by 4 matrix, until we get the identity on the left-hand side. The inverse of the matrix will then be equal to the matrix in the right-hand side. It must be noted that if the left-hand side cannot be reduced to the identity matrix, then the inverse doesn't exist for this matrix. We'll then perform the first row operation, which is a row multiplication operation. Next we'll perform a row add to make a leading one in the first column, which is a pivot column. Then we'll do another row multiplication operation on the second row. And finally we'll do the next row operation so as to give us the identity matrix. The inverse is then in the right-hand side of this matrix. This works because we're performing row operations on each of these halves of the matrix together, which is like multiplying each side by the same matrices. The row operations may be likened to multiplying a lot of row operation matrices by the augmented matrix, like this, so that the inverse is really the product of all of these row operation matrices. And this is what the answer is. We can multiply these matrices together as though the bar wasn't there to give us this matrix. So I hope that you've learnt something from this video and that it has helped you to understand matrices better. Let me know your thoughts and opinions in the comments. Click on like and subscribe if you like this video and have felt that you've learnt something from it. Thanks for watching.